Okay, hello. So we're now on the variation of parameters. So we're still on the methods of solution for higher order differential equations. So particularly a non-homogeneous higher order differential equations. So there are again two methods in solving non-homogeneous higher order differential equation. So one of which is the undetermined coefficient, and the other one is the variation of parameters. So as was mentioned before, the undetermined coefficient is limited to certain functions, so including algebraic, exponential, as well as for sine and cosine. However, the variation of parameters, so we'll have a sometimes it's a bit complex solution as compared to undetermined coefficient. However, so it could resolve a given higher order differential equation. So given that the resulting integrand or resulting function is integrable. So variation of parameters is defined as a way or method for computing a particular solution of the non-homogeneous linear second order, actually even a higher order differential equations. However, so since it uses the Wronskian method or uses the principles of matrices, the higher the order of the given differential equation, so the more complex its solution will be. So in finding the general solution of a higher order differential equation using variation of parameters, so the general solution, so y, is still equal to the complementary solution y of c plus the particular solution y of p. So y of c can be taken, so using the same method for homogeneous with constant coefficient, while the y of p, or the particular solution, so can be taken, so using this given formula. So that is the y of p would be equal to a certain variable u sub 1, y sub 1 plus u sub 2, y sub 2 plus u sub n, y sub n. So depending on what would be the order of the differential equation. So if it is a second order differential equation, so then it will end only to u sub 2. Okay, so the maximum so would be u sub 2, y sub 2. And then it increases as the order increases as well. So the y sub 1 here, y sub 2, as well as the y sub n, so that would be the solution of the homogeneous part of the differential equation. So this one is taken from the complementary solution, y sub 1, y sub 2, and then the y sub n. So while the variable u sub 1 up to u sub n, so that one can be taken, so using this formula. So for u sub 1, u sub 1 prime, so that would be equal to the Wronskian. Okay, so using the solution of the homogeneous part of the differential equation, so divide it with the w. Okay, or the solution or the Wronskian of all the solution of the given differential equation. And since that would be u sub 1 prime, so to get u sub 1, that is why we are using integration on this part. Okay, so because that is the one that we want, the u sub 1. Okay, so the u sub 1, the u sub 2 up to the u sub n. U sub 1 is integral of w sub 1 over w, u sub 2 is equal to the integral of w sub 2 over w, and u sub n is equals to w sub n divided with w. So that is on how to get the u sub 1, u sub 2 up to u sub n. So remember that y sub 1, y sub 2 up to y sub n, so those are the solution of the homogeneous part of the higher order differential equation. So once we were able to integrate that, so we're just going to substitute it and then multiply it with the solutions and then we'll be able to get the particular solution y sub p. Then we're just going to append that one with the complementary solution y sub c, so forming the general solution using the variation of parameters. But again, so how do we get the w sub 1 and w? For example, if I would have the general solution or the standard form of a second order differential equation, so which is non-homogeneous. So this is the standard form for the homogeneous part, and then the g of x, so which makes it non-homogeneous. In this case, so since this is a second order differential equation, so therefore there are two solutions here. So that would be the y sub 1 and the y sub 2. So since that is a second order differential equation, so y sub 1 so would correspond to the first solution, and then y sub 2 would correspond to the second solution. So this one is taken, so using the method for first or method for homogeneous with constant coefficient, the three cases that we have, the repeated roots, the distinct roots, as well as the complex roots. And then once we have the solutions, so in this case that is the y sub 1 and the y sub 2, so we will be forming the Wronskian or the matrix. Okay, and then we're going to find the Wronskian of that given matrix. So this is the same way that we use so in determining the linear dependency or independency of the given solutions. So the w then so can be taken so using on the first row, so that would be the solution. Okay, so y sub 1 and y sub 2 would correspond to the two solutions of the second order differential equation. And then the y sub 1 prime and the y sub 2 prime, so that's the first derivative. Okay, so the first derivative of the sets of solution. So since there are two solutions, so we will be only forming a 2 by 2 matrix. And then so that would correspond to our w. So in w sub 1, so since we're talking about the w sub 1, we're just going to change. Okay? So if you're familiar with the Kramer's rule, so we're going to use the Kramer's rule. And from there, so once we were able to form our w here, so we're just going to change the first column. So our first column so would be 0 and g of x. Okay, so the last row will always be our g of x, and any row above that g of x, so that would always make it 0. So we're just going to make it 0. So that is how we use the Kramer's rule. Okay, so we're just going to change. Okay, so we're just going to change the first column so by 0 and g of x. So 0 and g of x. So for w sub 2, so since we're talking about w sub 2, so this time around, so we're just going to retain the first column, which is y sub 1 and y sub 1 prime. And then we're going to change the second column. So since we're talking about the w sub 2, so the one that we will be changing so would be from y2 and y2 prime into 0 and g of x. Okay, so that is how do we get w sub 1 and w sub 2. And then once we have the w sub 1 and w sub 2, so we're just going to determine so what is the determinant, or what's the Wronskian. Okay, so the Wronskian of the w, so remember that is the downward, the product of the downward minus the product of the upward. So that is how we do it. So we're just going to find the determinant of the given matrix, or we're just talking about that one as the Wronskian method. And then afterwards, so we're just going to w sub 1, so divide it with w. So to get u sub 1. W sub 2 over w, that would give us the u sub 2. So what if it is a third order? So if it is a third order differential equation, so as you can see here, so there are three solutions. And then we still have the g of x there. So for our w then, so we're just going to write down the on the first row, so will be the three solutions. And then the second row would be the first derivative of those solutions, and then the third row would correspond to the second derivative of those solutions. So that is on how to get w. And then, so to get w sub 1, so just like what I mentioned before, so on the last row, we're just going to attach the g of x. And anything above the g of x, so we're just going to write down 0 and 0. Okay, so 0 and 0. So this is for w sub 1, so we're going to change the first column. And then we're just going to retain, as you can see here, the second row, column and the third column are just the same. So for w sub 2, so what we are going to change would be the second column. So the first column and the third column is exactly the same as the first and third column of the W, matrix W. And then for the w sub 3, so you can see here, so that would be on the third column. So where we are going to write the 0, 0, and g of x. Then the first two columns, so are exactly the same as the first two columns of the Wronskian W. Okay, so that is on how to form. Okay, so but this time around, this is a 3 by 3. Okay, so this is a 3 by 3. So since this is a 3 by 3, so the method on how to find the determinant or the Wronskian, so will be different on a 2 by 2. Okay, so just like what we did on the intro. Okay, so for higher order differential equations, so in determining the linear dependency and independency of the solution sets of a given higher order differential equation. So once we have this one, so in the same manner, so how to get u sub 1 prime or u sub 1, so that would be the integral of w sub 1 over w. Then u sub 2 would be the integral of w sub 2 over w. U sub 3, so would be the integral of w sub 3 over w. And afterwards, so we're just going to attach it. Okay, so with the solution, so forming the y sub p. Okay, so that is on how to find, okay, so the solution of a given higher order differential equation using variation of parameters. So for the sake of our discussion, so we are just going to limit our order of equations and up to third order. So that would be a 3 by 3. It's because when you are going to get, for example, if that would be a fourth order differential equation, that will become 4 by 4. So for a 4 by 4 matrix, so the method that we are using in getting the Wronskian of a 3 by 3 matrix is different, okay, with a 4 by 4 matrix. As you can see, the 2 by 2, the method for 2 by 2 is different with the method for 3 by 3. And in the same way, it's another method in solving a 4 by 4 matrix. Okay, so the solution for a 3 by 3 matrix is different with the solution of a 4 by 4 matrix. So actually that one will be discussed in advanced mathematics, but I think for aeronautical engineering, you don't have one. So we're just going to limit our discussion here. The idea for a 4 by 4 matrix to get its determinant or the Wronskian, so that is by the use of cofactor method. Okay, so which was not discussed here. So actually that is a topic for advanced mathematics. So that is why our examples, so even with activities, we are only limited up to a third order differential equation. Okay, so let's have our first example. So for example number 1, so we have y double prime minus 2y prime plus y is equals to e raised to x over 1 plus x squared. So as you can see here, so we have a second order differential equation. So it's non-homogeneous. And then the one on the right side is e raised to x all over 1 plus x squared. Although as you can see here, so the numerator so involves an exponential function, and then the one on the denominator is algebraic function. However, so if we're going to consult our table, so using the undetermined coefficient, there is no such case, just like this one. Okay, you cannot resolve. Okay, you cannot. Okay, so you cannot resolve this one. So using undetermined coefficient. So you can only resolve this one using variation of parameters. So just like on an undetermined coefficient, so we're going to start by getting the complementary solution. So that is changing the differential equation into its equivalent algebraic form. So that will be m squared, so minus 2m, and then plus 1 will be equal to 0. And this one is factorable, so m and m. So I think that would be a negative 1 and a negative 1. So that will give us a negative 2m and a positive 1. So therefore, so we can write here that m sub 1 is equals to m sub 2, and that would be equal to 1. And finally, so we could get our complementary solution to be c sub 1 e raised to, so our variable is x, so c sub 1 e raised to x. And then, so since this is a repeated root, so we'll have a c sub 2 x e raised to x. Okay? So that is our complementary solution, y sub c. So from here, our first solution then is e raised to x, and then our second solution is x e raised to x. So from here now, so we can now, we are now going to get our y sub p. Okay, so remember that since there are two solutions here, so our y sub p so will be equal to u sub 1, y sub 1, plus u sub 2, y sub 2. Okay, so y sub p is equal to u sub 1, y sub 1, plus u sub 2, and y sub 2. And as you can see here, we already have y sub 1 and y sub 2. We don't have the u sub 1 and the u sub 2. So to get the u sub 1 and u sub 2, so we need to find the Wronskian. Okay. So w then, so will be equal to, we're going to write our two solutions. So that is the first solution is e raised to x. And then the second solution is x e raised to x. So this one could interchange. Okay. So it is possible that x e raised to x would be y sub 1, and then e raised to x would be y sub 2. However, if you're going to do that, so make sure that if x e raised to x becomes y sub 1, so that is the one that you're going to substitute in this y sub 1. Okay, so in this y sub 1. So the next step is we're going to find the first derivative of the sets of solutions. So e raised to x, its first derivative, it's still e raised to x. And then for the second one, so product rule, so x e raised to x, so u is x. E raised to x, derivative of x is 1. And then plus, copy e raised to x, derivative of x, it's 1. So therefore, so we'll have this given matrix. And then we're going to find, so what is w? So W then, so will be equal to, so product, so e raised to x, so downward, so minus the upward. So e raised to x times x e raised to x is x e raised to 2x. And then ex times ex is plus e raised to 2x. And then minus upward. So minus e raised to x times x e raised to x is x e raised to 2x. And as you can see here, so this would cancel out. So therefore, we have w to be equal to e raised to 2x. So now that we have that, so we're going to get our w sub 1. So for our w sub 1, so our first column, so will be 0, and then the second row, so would be our g of x. So our g of x is e raised to x over 1 plus x squared. So this is our g of x. So e raised to x over 1 plus x squared. And then we're just going to write down our second row. So that is x e raised to x. The other one is x e raised to x plus e raised to x. So our w sub 1 then, so would be 0 times that, so would be 0, and minus xex times ex, so we'll have x e raised to 2x all over 1 plus x squared. So w sub 1 is just simply negative x e raised to 2x all over 1 plus x squared. So that is our w sub 1. And then for our w sub 2, so we're just going to copy the first column, so which is e raised to x and e raised to x. So previously we copied the second column. And then this time around, so we're just going to copy the first column, and then w sub 2, or the second column then, so would be the 0 and the g of x. So ex over 1 plus x squared. And w sub 2 then, so downward, so ex and ex is 2x over 1 plus x squared. Then minus upward, ex times 0 is 0. Or in short, w sub 2 is e raised to 2x over 1 plus x squared. So now that we have all the Wronskians, okay, the w sub 1, and the w sub 2, so we can now get what is u sub 1. So u sub 1 is the integral of w sub 1 over w. And for this instance, so w sub 1 is negative x e raised to 2x all over 1 plus x squared. Then our w is e raised to 2x. And e raised to 2x would cancel out to e raised to 2x. And thus, we'll just have this one to be the integral of negative x over 1 plus x squared. So of course, there should be dx there. And u here is 1 plus x squared, so du becomes 2x dx. And our neutralizing factor then, so would be 1/2. So therefore, our u sub 1 is equal to So we have negative there, so negative 1/2. And then that would be ln of 1 plus x squared. Okay. And for our u sub 2, that's the integral of w sub 2 over w. W sub 2 is e raised to 2x over 1 plus x squared. At the same time, w is e raised to 2x dx. So that would cancel out. So that will leave us to 1 over, I'm going to change that, x squared plus 1 dx. So this is familiar. So this would be, u sub 2 is just simply an arc tangent. Okay? An arc tangent of x. So now we have u sub 1 and u sub 2. So y sub p then is u sub 1, y sub 1 plus u sub 2, y sub 2. So our u sub 1 is negative 1/2 ln of 1 plus x squared. Then our y sub 1, so based from our solution, is e raised to x. Then plus u sub 2 is arc tangent of x. Y sub 2 is x e raised to x. And thus our y sub p would be negative 1/2 e raised to x and ln of 1 plus x squared and plus x e raised to x arc tangent of x. And finally, so our y would be y sub c plus y sub p. So y then would be equal to c1 e raised to x plus c2 x e raised to x, then minus 1/2 e raised to x ln of 1 plus x squared, then plus x e raised to x arc tangent of x. And that one will become our final general solution. And that is our first example. So let's move on with another example. So we have y double prime plus y is equals to secant theta tangent theta. So again, so we're going to get our complementary solution. So transform this one into its algebraic equivalent. So m squared, then plus 1 will be equal to 0. Then m squared will be negative 1. So m would be positive, negative, the square root of negative 1. So we're in m then would be positive and negative I. So from here, our alpha is 0, so our beta is 1. So therefore, our yc then so would be equal to, so c1 e raised to 0 is 1, and then cosine beta x. So cosine x, then plus c2, so we're using theta as our independent variable. So cosine theta, then plus c2 sine theta. So that is our complementary solution. So therefore, our y sub 1 is just simply cosine theta, and y sub 2 is sine theta. So we have our y sub c. So now we're going to get our Wronskian. So since there are two solutions, so that is cosine theta and sine theta. So derivative of cosine theta is negative sine theta. Sine is cosine theta. So downward minus upward. So cosine squared theta, then minus negative sine squared theta. So making it cosine squared theta plus sine squared theta. So therefore, W is equal to 1. Okay, so that's a Pythagorean identity. So for our W sub 1, our g of x is secant theta tangent theta. So that would be, this is 0, and secant theta tangent theta. Then just copy the second column, so sine theta and cosine theta. So we'll have downward is 0, then minus sine theta, secant theta, tangent theta. And that will make it so 0, that's negative sine theta. Secant is the same as 1 over cosine theta. Tangent is sine theta over cosine theta. So we could simplify this one. So negative sine squared theta all over cosine squared theta. So if we have sine squared theta plus cosine squared theta is equals to 1. So transposing the negative sine theta, so that would become cosine squared theta minus 1. Okay. So negative sine squared theta is the same as, remember this, that negative sine squared theta is equals to cosine squared theta minus 1. So I just manipulated the Pythagorean identity and then divide it with cosine squared theta. And simplifying this one, cosine squared over cosine squared is 1. Then minus 1 over cosine squared is secant squared theta. So that becomes our W sub 1. And for our W sub 2, so copy the first column, so which is cosine theta and negative sine theta. And then, so 0 and our g of x, secant theta and tangent theta. So this one would be equal to, so cosine theta, secant theta, tangent theta, then minus 0. However, so secant theta is 1 over cosine theta, then tangent theta. So this would cancel out, so leaving us to have W sub 2 to be equal to tangent theta. So now that we have all the Wronskian, so we can now get our U sub 1. So U sub 1 is the integral of W sub 1 over W. W sub 1 is 1 minus secant squared theta over W, which is just 1, and then d theta. So from there, so d theta, the integral of d theta is theta, and integral of secant squared would be tangent theta. So U sub 1 is theta minus tangent theta. So u sub 2 is w sub 2 over w. And that is w sub 2 is tangent theta over 1 d theta. So therefore, this is sine over cosine. So negative ln of cosine theta. So again, so y of p is u1 y1 plus u2 y2. So u1 is theta minus tangent theta. y1 is cosine. And plus y2 is negative ln of cosine theta. Y sub 2 is sine theta. So y sub p then, so is equal to theta cosine theta minus tangent is sine over cosine. So cosine would cancel out, so that would just leave us to have sine theta. And then minus, that is sine theta, multiplied it with ln of cosine theta. So that is our y sub p. However, so our general solution is y sub c plus y sub p. So y then, so c1 cosine theta plus c2 sine theta plus theta cosine theta minus sine theta minus sine theta ln cosine theta. However, so there are c2 sine theta and negative sine theta. So combining the two, so that would make it c1 cosine theta plus c2 minus 1, that would be sine theta, plus theta cosine theta minus sine theta ln of cosine theta. So we could introduce a new arbitrary constant there. So because c2 minus 1, it's still a constant. So therefore, y then would be c1 cosine theta plus c3 sine theta plus theta cosine theta minus sine theta multiplied it with ln of cosine theta. As you can see here, so we were only able to combine so those terms so with numerical coefficient. So in this case, that is c2 and the negative 1. Although c1 cosine theta is similar with theta cosine theta, so we could factor out cosine theta there. However, theta here is a variable. It's not a constant. So therefore, we're not going to combine them anymore. So in the same manner that we have sine theta here, so which is similar with c3 sine theta, but the problem is ln of cosine theta is not a constant. So it's a variable. So if it's just a variable, we're just going to leave it as is. And thus, so our general solution then, so would be y is equals to c1 cosine theta plus c3 sine theta plus theta cosine theta minus sine theta ln or ln cosine theta. Okay, so this is an example of a trigo function, but still it's a second order differential equation. So let's have example number 3. So y double prime plus 2y prime plus y is equals to e raised to negative t ln t. So this is a product of an exponential function and a logarithmic function. So for our g of t. Okay, so it's a g of t. So again, so m squared plus 2m plus 1 is equals to 0. This is m and m. I think a plus 1 and a plus 1 is equal to 0. So 2m, okay. And we could have here that m1 is equals to m2, and that is negative 1. So this is a repeated root again. So yc then would be c1 e raised to negative t plus c2 t e raised to negative t. Okay, so that is our complementary solution. So y sub 1 is e raised to negative t. So y sub 2 is t e negative t. So our w then, so for our two solutions, so e negative t, then t e negative t. So derivative of this is negative e raised to negative t, then t e raised to negative t, derivative of negative t is negative 1. And then plus, just copy e raised to negative t, derivative of t is just 1. So our w then, so will be a negative t e raised to negative 2t plus e raised to negative 2t. Then minus negative t e raised to negative 2t. And that would become positive. And thus, the 2 would cancel out. So our w then, so would be equal to e raised to negative 2t. For our w sub 1, so 0, then we're going to attach our g of t. That is e raised to negative t ln t. And then, so t e negative t, negative t e negative t plus e negative t. So this is 0 and minus t e raised to negative 2t ln t. So negative t e raised to negative 2t ln t. Okay, so our w sub 1 would be negative t e raised to negative 2t ln t. And for our w sub 2, this e raised to negative t, negative e raised to negative t. So copy the first column. And then our second column, so would be our g of x, e negative t ln t. So downward, so we'll have e raised to negative 2t ln t, then minus 0. Or w sub 2 is e negative 2t ln t. So now that we have that, so we can now compute for u sub 1 as the integral of w sub 1 over w. So since that is in terms of t, so w sub 1 is negative t e negative 2t ln t divided with w, so which is e raised to negative 2t dt. So forming, yes, this one would cancel out. So we'll just have negative t ln t dt. So to resolve this one, we could use by parts. So liate. So we'll start with u to be ln t, and then our dv is negative t dt. So du would be ln t, so it's just dt over t. And then our v then, so negative t squared all over 2. So our u sub 1 then would be equal to uv. So negative t squared all over 2 ln t and minus v du. So minus, so v is still negative, so that would make it plus the integral of t squared over 2, so times dt over t. U sub 1 is negative 1 half t squared ln t, and then plus 1 half integral of, so t squared over t is t dt. Or u sub 1 would be negative 1 half t squared ln t plus integral of t is t squared all over 2. So that would be 1/4 t squared. So negative 1 half t squared ln t plus 1/4 t squared. That is u sub 1. For our u sub 2, integral of w sub 2 over w. W sub 2 is e negative 2t ln t. So e raised to negative 2t ln t all over w, which is e raised to negative 2t and dt. So that would cancel out. That is just ln t dt. So our u there is still ln t. du is dt over t. dv is dt and v is t. So therefore, u sub 2 is uv. So t ln t minus integral of v du. So t times dt over t. So wherein t would cancel out. Or u sub 2 is t ln t minus the integral of dt is just t. Therefore, so for our y of p, that is u sub 1, y sub 1, plus u sub 2, y sub 2. So y sub p then, our u sub 1 is negative 1 half t squared ln t plus 1/4 t squared. Y sub 1 is e raised to negative t. Then plus u sub 2, which is t ln t minus t, and t e raised to negative t. So y sub p then would be negative 1 half t squared e negative t ln t plus 1/4 t squared e negative t plus t squared e negative t ln t minus t squared e negative t. So combining similar terms, so t e negative t ln t, so this is t squared e negative t ln t. So that is 1 minus 1 half, that is 1 half. So 1 half t squared e negative t ln t. And then 1/4, so this should be t. So t squared, so 1/4 minus 1, that is negative 3/4 t squared e negative t. Our general solution then, that is y is yc plus yp. So y is yc And C1 e negative t plus C2 t e negative t. And plus 1/2 t squared e negative t ln t minus 3/4 t squared e negative t. Okay, so no similar terms. So C1 e negative t plus C2 t e negative t plus 1/2 t squared e negative t ln t minus 3/4 t squared e raised to negative t. Okay, so that is our third example. So for variation of parameters. So we have a bit longer solution but still manageable. So for our third example, so we have another variation for our examples. So that would be our fourth one. Number 4 is an IVP problem. So for y double prime minus y is equals to x e raised to x over 2. And then when x is 0, y is 1. And then when x is 0, y prime is 0 as well. So y prime of 0 is equals to 0. So it's an IVP problem, a second order differential equation. When using variation of parameters, so take note of this. So this is a special case. If you have noticed on our previous examples, so in our first example, the numerical coefficient here is 1. For our second example, again, the numerical coefficient of the highest derivative is 1. For our third example, the numerical coefficient of the highest derivative is 1 as well. So that is why we're just solving it the way we usually solve it. But on this particular example, the highest derivative of y double prime, its numerical coefficient is 4. Okay, so it's not 1. So in solving using variation of parameters, we have to make sure that the numerical coefficient of the highest derivative should always be 1. So otherwise, we will arrive into a different solution. Okay, so we will arrive into a different answer. So that is why our first step here is we are going to remove, okay? We're going to remove the numerical coefficient, so by multiplying everything by 1/4. So that this will change into y double prime minus y over 4 is equals to x e x over 2 all over 4. Okay, so y double prime minus y over 4 is equals to x e raised to x over 2 all over 4. And afterwards, that is the time that we're going to proceed with our usual way. So transform this one into algebraic, so that is m squared minus, it's just 1/4, so equals to 0. And then m squared will be 1/4. So m then would be positive, negative the square root of 1/4. So we have m1 to be positive 1/2, and m2 is negative 1/2. So therefore, our y sub c is c1 e raised to, so we're using x over 2, and then plus c2 e raised to negative x over 2. So c1 is e raised to x over 2 plus c2 is e raised to negative x over 2. So we have our y of c. So our y1 is e raised to x over 2, and then y2 is e raised to negative x all over 2. So w then will be e raised to x over 2 and e raised to negative x over 2. So derivative will just be 1/2 e raised to x over 2, and then this is negative 1/2 e raised to negative x all over 2. So the Wronskian then will be negative 1/2. So e raised to 1/2 minus 1/2 is 0. And then minus 1/2, e raised to 1/2 minus 1/2 is still 0. So e raised to 0 is 1. So giving us to be negative 1. So w is equals to negative 1. And then for w sub 2, our g of x is x e raised to x over 2 all over 4. So 0, x e raised to x over 2 all over 4. Correct? So, okay, it's correct. And we're just going to copy e negative x all over 2 and negative 1/2 e raised to negative x all over 2. So downward is 0, then minus e raised to x over 2 times e raised to negative x over 2. So 1/2 minus 1/2 is e raised to 0, so which is 1. So simply put, so this would just be equivalent to negative x all over 4. So w sub 1 is equals to negative x all over 4. So this is w sub 1. Then for our w sub 2, so e raised to x over 2, then 1/2 e raised to x over 2, 0, x e x over 2 all over 4. So this will be, so x, 1/2 plus 1/2 is 1. So x e raised to x all over 4. And that is w sub 2. X e raised to x all over 4. So for our u1 would be w sub 1 over w. W sub 1 is negative x all over 4, where w is negative 1 dx. Just simply 1/4 the integral of x dx. Or that would be x squared all over 2, so 1 over 8 x squared. So that is u1. So for u2, w sub 2 over w, x ex all over 4 all over negative 1 dx. Or that will just be a negative 1/4 and the integral of x e raised to x dx. So we could use tabular method. So x and e raised to x. This is 1. This is integral is e raised to x, 0, e raised to x. So positive and negative. So u sub 2 then would be negative 1/4. Multiplied it with x e raised to x minus e raised to x. Or just simply negative 1/4 x e raised to x plus 1/4 e raised to x. That is our u sub 2. So our y sub p is u sub 1, y sub 1, plus u sub 2 y sub 2. U sub 1 is 1/8 x squared, 1/8 x squared, and y sub 1 is e raised to x over 2. Then minus u sub 2, negative 1/4 x e raised to x plus 1/4 e raised to x. Then this is e raised to negative x all over 2. So this should be plus. So 1/8 x squared e raised to x all over 2 minus 1/4 x. So 1 minus 1/2 is 1/2. So x all over e raised to x all over 2. And then that would be plus 1/4 e raised to x all over 2. So y is yc plus yp. Y then would be equal to yc is c sub 1 e raised to x all over 2 plus c sub 2 e raised to negative x all over 2. Then plus 1/8 x squared e x all over 2 minus 1/4 x e raised to x all over 2 plus 1/4 e raised to x all over 2. But remember, c1 e raised to x over 2 and 1/4 ex over 2 can be combined. And thus, c1 plus 1/4. So we could have a new arbitrary constant c sub 3. So c sub 3 e x over 2 plus c sub 2 e raised to negative x all over 2 plus 1/8 x squared e raised to x all over 2 minus 1/4 x e x all over 2. However, so this is an IVP problem. So when x is 0, so initially when x is 0, y is 1. So when x is 0, y is 1. So we can substitute. So y is 1, c3, e raised to 0. Okay, so e raised to 0 is 1. Then plus c2, e raised to 0 is 1. Plus, we have x squared there, so everything will be 0. Minus, we have x there, we have 0 as well. So from here, so we can write that c2 plus c3 is equals to, we could start with c3. Okay. So actually whichever. c3 plus c2 is equal to 1. So that is our equation number 1. However, so when x is still 0, y prime is 1. So I need to derive my general solution. So y is y prime c3 e raised to x over 2. So derivative of x over 2 is 1/2. So 1/2 c3 e raised to x all over 2 minus 1/2 c2 e raised to negative x all over 2. And then, so for simpler solution, so I'm going to combine these two. So this would make it 1/8 x squared minus 1/4 x. So multiplied it with e raised to x all over 2. So that I could use product rule. So u then, so would be plus 1 over 8 x squared minus 1/4 x. So derivative of e raised to x all over 2. So we'll just have 1/2 there. And then plus the derivative of the algebraic. So that is 1/8 times 2. That is 1/4 x. Then minus 1/4. Then copy ex all over 2. The derivative of the algebraic is 1/4 x minus 1/4 e raised to x all over 2. Okay. So now that we're done, so we're going to substitute. So y prime is 1. E raised to 0 is 1. So therefore, I'll have 1/2 c3. Then minus 1/2 c2. E raised to 0 is 1. Okay. And next is, so we have x squared. So which is 0. X is still 0. So therefore, the whole of that is 0. So plus 0. And plus 1/4 times 0 is 0. Minus 1/4 times 1. So we'll just have a negative 1/4 there. So we have 1/2 c3 minus, for our initial value, so we have here that when x is 0, y prime is 0 as well. So that should be 0. So this is 0 as well. And then this is 0. So therefore, I'll have it here to be 1/2 c3 minus 1/2 c2. C2. Then transposing it, so that would be 1/4. So multiplying everything by 4, I'll have 2c3 minus 2c2 is equals to 1. 2c3, 2c2 is equals to 1. And then I have equation 2. So multiplying equation 1 by 2. So that would give us 2c3 plus 2c2 is equals to 2. And then for our second equation, we have 2c3 minus 2c2 is equals to 1. So adding the 2, I'll have 4c3. So this is 0 is equals to 3. So giving us c3 to be equivalent to 3 over 4. And then we have c3 plus c2 is equals to 1. So c3 plus c2 is equals to 1. So therefore, c2 is equals to 1 minus c3. So if c3 is 3/4, so 1 minus 3/4, that is 1/4 for c2. So therefore, so for our final solution, so let me copy. So supposedly, so this is the general solution. So our particular solution then, so would be yc3 is 3/4. So 3 over 4 e raised to x all over 2. C2 is 1/4. So plus 1/4 e raised to negative x all over 2 plus 1 over 8 x squared e raised to x all over 2 minus 1/4 x e raised to x all over 2. And That will be our particular solution. Okay, so that's on how to find or solve an initial value problem. So there are two initial values that are given. So if it is a second order, if it is a third order, there are three initial values which are given. Okay, so that is a variation of this given example. So it is an IVP problem. So for problem number 4. So for our last problem, or last equation, so we'll have a third order differential equations. So y triple prime plus 4y prime is equals to secant 2x. So again, the numerical coefficient there is 1, so we're just going to leave it as is. And then this would be m cubed plus 4m is equals to 0. So we could factor out m, so m squared plus 4 is equals to 0. So we'll already have m1 to be 0. And then m squared is equal, or m squared plus 4 is equals to 0. So m squared would be negative 4. So m then would be positive negative the square root of negative 4. Or that is just positive negative square root of 4 is 2. Then negative 1 is I. So positive negative 2i. So alpha is 0 and beta is positive 2. Our y sub c then so would be, so c1 e raised to 0 x, it's just 1. So c1 plus c2, so we don't have exponential function, so c2 cosine 2x, then plus c3 sine 2x. So our y1 is 1, our y2 is cosine 2x, and then y3 is sine 2x. So w then, so we could write down our three solutions. So that is 1 cosine 2x and sine 2x. So derivative of 1 is 0, 0. Derivative of cosine is negative sine 2x. Derivative of 2x, that is 2. And then sine 2x is cosine 2x and then times 2. Then derivative of sine is cosine 2x. So 2 times negative 2 is negative 4. Derivative of cosine is negative sine 2x. So 2 times 2 will have negative 4 sine 2x. And then so we could have our w. So this is our first term. That is 1, negative 2 times negative 2. That is positive 8. Then sine 2x, and sine 2x is sine squared 2x. And then for our second, so this is cosine 2x, negative cosine, however, is multiplied with 0. So therefore that is plus 0. And then the next one we have this one. So 0 multiplied with 4, multiplied it with sine. So therefore that is still 0. Then minus upward. Okay. For our upward, that is 0. plus this one. So 1 times negative 4 and negative 2. So that is negative. Negative 8 cosine squared 2x. And lastly, that would be 0. So plus 0. So we have then, 8 sine squared 2x. So negative and negative plus 8 cosine squared 2x. So we could factor out 8. So sine squared 2x plus cosine squared 2x. So this one is again a Pythagorean identity, which is equivalent to 1. So therefore, W is just simply equal to 8. For W sub 1, so we're going to change our first column. So our g of x is secant 2x. So 0, 0, secant 2x. Then copy the first two columns. So cosine 2x, negative sine 2x, negative 4 cosine 2x. Sine 2x, 2 cosine 2x, negative 4 sine 2x. So downward, we'll have 0, negative sine, negative 4. So that is 0. Cosine, 2 cosine and secant, I'll have plus 2 cosine squared 2x, secant 2x. And lastly, so we'll have 0. So plus 0. Then minus upward, so I'll have negative sine, that should be 2. Negative upward, so negative 2 sine squared 2x, secant 2x. And then 0. The other one, 0 as well. So leaving us to have, so we could have it as 2 cosine squared 2x, secant 2x, then plus 2 sine squared 2x, secant squared, or secant 2x. Just simply 2 secant 2x cosine squared 2x plus sine squared 2x. Again, this is 1. So therefore, W sub 1 is 2 secant 2x. Our W sub 2 we have 1, 0, 0, and then second column, so it will be 0, 0, secant 2x. So as you can see, the more zeros that we have here, so the lesser the complexity of our solution. Then for our third column, so we have sine 2x, 2 cosine 2x, negative 4 sine 2x. So this will be, so the first one is 0, second is 0, the third is 0. So it's all in all 0. And minus, upward is 0, middle, the second is 0 as well. And lastly, we just have 2, so plus 2. I'm just going to write it down below. So plus 2 cosine 2x secant 2x. We just have a negative 2 cosine 2x secant 2x. However, secant 2x is 1 over cosine. So negative 2 cosine 2x, 1 over cosine 2x. So that would cancel out. So therefore, our w sub 2 is just equal to negative 2. And lastly, so we have 1, 0, 0. The one in the middle is cosine 2x. Negative 2 sine 2x. And lastly, negative 4 cosine 2x. And 0, 0 secant 2x. So downward, we'll have negative 2 sine 2x secant 2x. Then this one, 0. The last one is 0. And minus, upward is 0 in the middle. The one below is 0. And the one above is 0. So we just have negative 2 sine 2x secant 2x. Again, negative 2 sine 2x. So secant is 1 over cosine 2x. So negative 2 sine over cosine is tangent 2x. So that is w sub 3. So for our u sub 1, that will be the integral of w sub 1 all over w. W sub 1 is 2 secant 2x. 2 secant 2x all over w is just simply 8. No, that will be 2 over 8 is 1/4. The integral of secant 2x dx. So this is 1/4 times integral of secant is ln, right? So ln of secant of 2x plus tangent of 2x. And then of course, derivative of 2x is 2 dx. So we'll have a neutralizing factor of 1/2. And thus, u sub 1 is 1 over 8 ln of secant 2x plus tangent 2x. Our u sub 2, w sub 2 over w, it's negative 2 all over 8. And that would be dx. And that would just be negative 1/4 dx. So just simply u sub 2 to be equivalent to negative 1/4 x. U sub 3 is w sub 3 over w. Negative 2 tangent 2x, negative 2 tangent 2x all over 8. That is negative 1/4 integral of tangent 2x. That is negative 1/4. Tangent is sine over cosine. So we'll have ln of cosine 2x. However, that is negative. And then neutralizing factor is 1/2. Or just simply 1 over 8 ln of cosine 2x. So that is our u sub 3. So our yp then would be u sub 1, y sub 1, plus u sub 2, y sub 2, plus u sub 3, y sub 3. Y sub p, our u sub 1 is 1 over 8 ln of secant 2x plus tangent 2x. Our y sub 1 is just 1. Then u2 is minus 1/4 x. And then our y sub 2 is cosine 2x. Then lastly, so plus 1 over 8 ln of cosine 2x, multiplied it with sine 2x. Or yp would be 1 over 8 ln of secant 2x plus tangent 2x minus 1/4 x cosine 2x plus 1 over 8 sine 2x ln of cosine 2x. One 8 minus 1/4 plus 1/8. And finally, so our y would be yc plus yp. So y then would be c1 plus c2 cosine 2x plus c3 sine 2x and plus 1 over 8 ln of secant 2x plus tangent 2x minus 1/4 x cosine 2x plus 1 over 8 sine 2x ln of cosine 2x. And that will be the final general solution. So for variation of parameters. Thank you.